So my name is Deedee Lavinder, and I am very happy to be here. I'm a back-end engineer at Spreedly in North Carolina, and I work in the payment space. And thanks, May. I'm also a director for our local chapter of Women Who Code, and I'm very excited to talk about encoding today. Who loves encoding? Yes, some enthusiasts. Okay, I saw some head shaking. Who can't stand encoding? Okay, more hands. All right, hopefully the numbers will look slightly different at the end. That's what I'm hoping. So even though entire books have been written about this topic, I'm hoping to spend the next 30 minutes or so covering some history and some foundational concepts, a little bit of Ruby-specific basics. And this is a topic that, for me, a little bit of understanding really went a long way. I'm hoping that's also true for you. So of course, the idea for this talk came from a bug that I encountered. How many of you have seen examples that could be included here? I learned a kind of interesting word for this in Japanese, which is majibake. Has anybody heard that word before? It basically means an unintelligible sequence of characters. As I dug in and started troubleshooting, I discovered some interesting things about encoding and its history, and they were super instrumental in helping me debug this issue. So recognizing that we may have a wide range of experience in the audience, let's start at the very beginning and define the word encode. To encode something simply means to convert it into a coded form. This concept has existed long before computers. The purpose of encoding is to transform data so that it can be properly and safely consumed by or understood by a different type of system. Morse code, for example, uses dots and dashes of sound or light along with varying length pauses to communicate certain characters over long distances. Another example of encoding that we're all familiar with is Braille, where physical raised bumps represent letters and symbols. The goal is not to keep information secret, but rather to ensure that the information is able to be properly consumed or understood. So encoding is not the same as encryption. These terms are sometimes mistakenly used interchangeably. While they both transform data into another format, encoding uses publicly available schemes that are intended to be reversed. This is the key distinction. Decoding only requires knowing which scheme was used to encode. You can think of it like a map or a legend or even a table. Encryption, on the other hand, is meant to protect valuable or sensitive information, and decryption is more complicated. Data is transformed using mathematical algorithms and a secret key, and the intention is that it not be easily reversed. You all have seen this one, oldie but goodie. We know that computers use binary code comprised of the digits 0 and 1 to store data. And to communicate with computers, we have to understand the basics of binary code. That smallest unit of data, a 1 or a 0, is called a bit. And groups of 8 bits are called bytes. Here are 4 bytes. And this numerical system, binary, maps to all other numerical systems. The way you get from binary to our familiar decimal or base 10 system is super fun and involves powers of 2. So with 8 bits and 1 byte, each bit has 2 possible values, a 1 or a 0. There are 256 possible combinations of those 8 bits. 2 to the 8th is 256. Isn't this cool? Okay. So, if you're new to binary, here is the explanation of the earlier reference to types of people. Can you see it there? The 2 decimal equals the 1 0 in binary. So using a number system translation, encoding schemes allow us to communicate or share data with computers. It translates those 1s and 0s into a system or language that we understand and can process. It's basically a set of mappings between the bytes in the computer and the numbers that we understand. After we go from binary to decimal, then we can map those familiar decimal numbers to our writing system or the characters of our language. This is how we communicate with computers. Understanding the language of computers means we translate those ones and zeros into our language or mode of communication. Let's see if my fanciness will work. So I want you to take a look at this hexadecimal system. It's often referred to simply as hex. The decimal part is important, though, to understand this number system. Hex means 6, and decimal means, of course, 10. And 6 plus 10 is 16. So this is represented by the digits 0 through 9, and then the letters A through F. Converting from decimal to hexadecimal is super fun and involves dividing by 16 using integers, and then recording the remainder in hexadecimal until you get to 0. The final hexadecimal value is the digit sequence of those remainders from last to first. Okay, we're not going to get super into the weeds on hexadecimal, but it will come up again a bit later. So in the beginning of the computer age, as it were, there were no shared standards for how to map binary to language. There are many unremembered encoding schemes from those early days of computing. Of course, intercompatibility eventually became increasingly important, and in 1960, the organization we now know as ANSI, or the American National Standards Institute, began working on the American Standard Code for Information Exchange, which we know as ASCII. So first published in 1963, ASCII uses 7 bits to encode 128 specified characters. Remember that 2 to the 7th equals 128. Of those 128 possibilities, 95 of the encoded characters are printable. They include the digits 0 to 9, uppercase and lowercase letters A to Z, and a handful of punctuation symbols. The original ASCII specification also included 33 non-printing control codes. Those are mostly obsolete now. There were many other encoding schemes at the time. One notable encoding scheme was the EBCDIC, or Extended Binary Coded Decimal Interchange Code. It's a mouthful. That was used extensively in the early days by IBM. But the difference between ASCII and the EBCDIC is that ASCII allowed for the ordering and sorting of lists alphabetically. And this was key, and eventually ASCII won out as the more widespread choice. So here's an example of ASCII encoding. Each byte represents one letter or character. Now, remember how I said that ASCII only uses 7 bits? That 8th bit was unassigned. It was extra. And if you put that 8th bit to use, it would actually allow for another set of 128 possible byte configurations to be assigned to different characters. And so even though ASCII, the first 128 was pretty uniform, people started making up for what was missing in that original ASCII set. Letters from other languages with accents or different shapes, the pi sign. And there are apparently hundreds of different ways that programmers use those extra ASCII slots for the characters they needed. But again, this produced a lot of compatibility issues. So meanwhile, ISO 8859 was attempting to provide encoding schemes for languages other than English. And in fact, encodings for all the languages were being developed. Russian, Hindi, Arabic, Korean, and all the other languages in active use on our planet. Not to mention the ones not in use anymore, Latin and hieroglyphics. Imagine trying to write a mixed language research document. It became clear that 1 byte per character would never be sufficient. Chinese and Japanese both contain tens of thousands of characters. So multi-byte encodings were created. Here's an example of a 2-byte encoding with 16 bits. This is a very small snippet from GB 18030, which is an encoding that covers traditional and simplified Chinese characters. Using 16 bits, or 2 bytes, it's possible to encode 65,536 distinct values. Now we're talking. Except it was just yet another specialized encoding format among many. Look at this list. It's intentionally super small so you can't read it. Things were getting really confusing, and the compatibility issues were compounding. In the late 80s, the concept of a new character encoding scheme that could handle any character on any computer emerged, and Unicode was invented. The first version was introduced in 1991, and it adds a layer of abstraction to the process by assigning a code point to every conceivable character. It is a ginormous table of over 1 million possible code points that can be used to represent all the character sets. Middle Eastern, Far Eastern, European, prehistoric, future characters we haven't invented or maybe even discovered. Using Unicode, you can write a document containing virtually any language, using any character you can type into a computer, including Klingon and, of course, emojis. As of May 2019, the most recent version, Unicode 12.1, contains a repertoire of 137,929 characters. And there are plenty of code points still available for additional characters. So if you're thinking about writing a new writing system, coming up with a new language, don't worry, Unicode has room for you. Now, a common misunderstanding is that Unicode is an encoding. It is not. It does not specify how to store numbers in a file. It's not binary code. It's another layer another layer of abstraction that sits between our understanding of a character or a letter and the bytes that the computer uses to represent that character. So here's an example of an African writing system or a writing script used to transcribe the language in Somali. You can think of Unicode code points as an association with or a legend of characters. Actually, sometimes a character will even have more than one code point. And here's where hexadecimal comes up again. Unicode points are in hexadecimal. You can see in the top right corner. This is a shorter way to reference large numbers. Now, in our thinking, as we move towards a deeper understanding of encoding, it's important to keep separate the characters, which are kind of abstract, right? What is A, lowercase, uppercase, etc., represented by the Unicode code points, and the actual encoding, which is the sequence of bytes that represents those code points. Now, there are several encodings for Unicode, and they exist under an umbrella called Unicode Transformation Format, or UTF. 3 of the most popular UTF encodings are UTF-32, UTF-16, and UTF-8. They can all encode any Unicode code point or character. The difference is in how much space or how many bits they take to do it. UTF-32 uses 4 bytes, hence 32 bits, for every code point. UTF-16 uses between 2 and 4 bytes, and UTF-8 uses between 1 and 4 bytes per character. I hope you're not surprised to hear which is the most popular encoding, UTF-8. Now, this graph is dated, but I can tell you that the trajectory has not changed. Since 2009, UTF-8 has been the dominant encoding of any kind, not just Unicode encodings. And in 2019, UTF-8 encoding accounts for more than 94% of all web pages. And the percentage is even higher for like the most popular 1,000 web pages. So UTF-8 has become so popular for several reasons. The first is that UTF-8 is backwards compatible with ASCII. So that means that in most situations, it just works. And remember when we said that UTF-8 uses between 1 and 4 bytes per character? That variability means space is saved over using an encoding which always uses 2 or 4 bytes, like UTF-16 or UTF-32. It also avoids complications relating to endian, sorry, this word just completely got out of my head, endianness, and byte order marks, which are required for UTF-16 and UTF-32. Okay, let's talk about this word, which I just had trouble saying, endianness. In the context of encodings, this refers to the order of bytes in a multi-byte representation of a character. Computers, like people, can read left to right or right to left. And when reading a multi-byte character representation, these two options are known as little endian and big endian. Isn't that cute? Okay, little endian is where the bytes are stored in order from least to most significant. So the way we write dates can illustrate a similar kind of ordering. In Europe, for instance, dates are written as day, month, year. I just lost my place here. Now, if you're, some folks are like in the little endian camp, and then other folks are in the other camp, which of course is known as big endian. And somewhat obviously, the opposite is true, where the bytes are ordered from most to least significant. So another date comparison would be ISO dates, which are written in a year, month, day format. So if your computer was set to read binary based on big endian, and it's also known as high endian or low endian, it would be unable to correctly parse something which had been encoded using a little or low endian format. So the endianness, again, refers to the ordering of bytes only within a multi-byte value. For characters that are represented by a single byte, like ASCII, the order obviously doesn't matter. So when it does matter, there are two solutions. You can either agree on a common format, easier said than done, or you can use something called a BOM, or a byte order mark. So the byte order mark just communicates whether your format matches or not by either being displayed correctly or backwards. If it's backwards, then you need to switch yours so that it will match. Now, the topic of endianness came up because this is one of the things that has really helped UTF-8 become so popular. It is not endian dependent. The order in which you interpret the bytes in each UTF-8 character encoding does not depend at all on the processor architecture, unlike UTF-16 or UTF-32. UTF doesn't encode a code point as a single integer. It encodes it as a sequence of bytes with a particular order, and where some of the bits are used to represent the code point, and some of them are just used to represent whether you're looking at the initial byte or a continuation byte. So that's kind of a cool thing about UTF-8. Now, Unicode is a brilliant solution to what was a really sticky problem, but it isn't perfect. The Unicode consortium can decide what to add or change, and sometimes their choices are hard to understand. For instance, they decided to unify these characters with a common origin called the Han glyphs, as the sample shows. We have plenty of code points. Why did these need to all be merged? It has caused some consternation and difficulty for the folks wanting to use these characters. And there are other issues as well. That variable width encoding isn't suitable for every application, and it isn't always clear how big a set of characters will actually be. Another thing is that converting between UTF encodings is not easy at all. So the other thing is that not all languages are getting the same level of attentiveness and inclusion, so this is problematic. But to be clear, it's really the best solution we have at the moment, and I am a fan. It's super interesting, and I'm curious to see what the next 10 or 20 years will bring in terms of encoding. Okay, so now I'd like to revisit something I said earlier, which is that decoding only requires knowing which scheme was used to encode. I just wanted to remind you of that important sentiment as we zoom in and take a look at Ruby specifically. So Ruby has an interesting history with regard to encoding. Some of you may have firsthand experience with the encoding frustrations experienced by many as Ruby transitioned from ASCII to UTF-8 in versions 1.8 and 1.9. Since 2.0, UTF-8 has been the default source encoding, and this has helped immensely. Now, there are a handful of methods in Ruby that can help us figure out what we need to know about the computer's bits and how they are, or have been, or will be encoded. So I kind of rearranged this section of my talk a bunch of times because I wasn't sure what to talk about first. But I finally settled on these two methods kind of being the ones I wanted to highlight. Understanding the difference between them was the turning point for me in feeling like I could untangle my encoding issues. These are the main two methods that Ruby uses to change data encoding. The first one, encode, actually alters the underlying bytes of a string to be a specific encoding or to change from one encoding to another. So that's a really critical thing to understand. Force encoding, and again, naming is hard. Force encoding does not alter the underlying bytes at all. Instead, it interprets the string using a different encoding scheme. So this is really critical, this distinction, knowing when to use these. Encode actually changes your data. So that's something to keep in mind. So here's an example. So here's the string. My original bug had to do with language from the Scandinavian region, and so I've chosen the name of this town to show you how encode can change things. So we call encode on this string. Now I'll tell you that the string was a UTF-8 string to begin with, but we're actually changing those underlying bytes to be the ISO 8859 encoding. And you can see what happens. Things get a little wonky. Now, if we change it back to UTF-8, which it's supposed to be, then it's fine. It's represented as it should be. And you can see when we call byte size on these two different strings that they actually have a different number of bytes. So understanding this was like the key for me to solving my encoding bug. Our app was calling encode on a response, and it was changing the underlying bytes. When you do that, there's no going back. If you're not preserving your original data and you change those underlying bytes, you can never get back to what you had. So that's something to remember before using this method. Changing the encoding to UTF-8 won't help you then if you've lost that original data. So understanding bytes as something apart, something different from the string representation of those bytes is key. You can also see that I called byte size on these strings. These method names are so fun. You can also call byte or bytes, and in Ruby, this will actually return the decimal value corresponding to the binary value, so I'll show you that. Using the same string from the previous slide, we called bytes, and we can see its actual 15 decimal bytes that correspond to the binary. There are some other fun methods that you can experiment with, and like with anything in Ruby, I would recommend going to your console, IRB, and just messing around with it. Find some crazy text from the internet and paste it in and see what you can do. So if you have just one byte, you see we got the first byte there, you can call CHR as a method on it, and it will return the character associated with that byte in the encoding that it is specified. Of course, if you have a character, then you can call ORD and get the byte returned. And for any string, you can ask what's the encoding. There's also another method that you can chain on there, .name, if you need it to be user-friendly. ASCII compatible is a nice one. Is this encoding valid? That could be really helpful. So these are just some suggestions for ways to sort of help you troubleshoot if you're in a tricky encoding spot. There are also some file level things to think about. We talked about Ruby's default source encoding being UTF-8 since 2.0. If you're using an older version, though, or you aren't sure that you can always check using the default external. Now, there may be times where you're dealing with files that have a different encoding than your system's default, and default internal will come in handy for that. Both of those also have setter methods if needed. The magic comment I wanted to just highlight, if you need an encoding to be different for one file, you can include this magic comment on the first line or second line if you have a line with a shebang. And then, of course, if you're writing code that produces or evaluates content for the web or in an email, this is where you want to be really sure that you are specifying and validating the encodings that you're using and that you want to accept. Because if you don't know the encoding of some piece of data that you've received, how will you decode it? For web pages, set that meta tag immediately after opening. Some of this is like standard practice, but just reminding you that it's like related to encoding, and if you're having encoding troubles, these are things to check. Also, if you're working on a web app with a database, you can actually set the encoding for your database. Don't forget to do that. Again, compatibility is crucial. To accurately decode something, you have to know the scheme that was used to encode. When troubleshooting, it's also important to think about the gems that you're using and the encoding schemes that they're using and what the content is that they're producing or sending to you. This actually was also related to my bug. The response body was coming back as ASCII 8-bit, which is like a whole nother kind of encoding. And even though my request had specified the character set UTF-8, so that's like a sneaky little thing to look out for. Okay, we are almost there. A discussion about encoding would not be complete without mentioning base 64. Do we love base 64? So fun. Okay, we get to go back to the bits. This is super cool. Base 64 is basically an encoding for encodings. It takes binary data and turns it into an ASCII string. It doesn't care about the encoding of the original data. It's only looking at the bits that are being used by the encoding. So the goal of base 64 is to be able to safely transfer information from one system to another without losing data. It does this by using this set of 64 characters that are common to most encodings, not most characters. Do you hear the difference? Did you notice that the Unicode code points are all in ASCII-friendly characters? This is why base 64 works. So the 64 characters include upper and lowercase letters A through Z, so that's 26 plus 26 is 52, plus the 10 digits, that brings us to 62, and then the forward slash and the plus sign. That's it, grand total 64. So the chart on the left shows the mapping between base 64 and binary. See how that binary is only 6 digits? Remember 2 to the 6th is 64. Powers of 2, so cool. Okay, so let's look at the bits. If you look at the chart on the right, you can see 3 letters that spell out MAN with their ASCII representations just below that. And of course, the ASCII representation is 8 bits assigned to each letter, right? 1 byte per character. Base 64 takes those 24 bits and groups them instead by 6. Base 64, 2 to the 6th, 64, so great. So if the bits that you want to base 64 encode don't divide evenly by 6, then equal signs are used for padding at the end. Has anybody happened to notice equal signs at the end of a base 64 thing? It's padding to make up that last block of 6. Okay, so in Ruby, base 64 is a module, and as such, it needs to be required. And when you call encode 64 on a string, line feeds are added to every 60 encoded characters, unless you call strict encode, in which case they're left out. Anybody ever wonder what that strict was about? If you're calling encode, it's so that it doesn't add those new line characters. When you call decode 64, characters that aren't in the base 64 original set will just be ignored. If you call strict decode, it will raise an argument error. That's how strict can help you in your base 64 calls. There's also something else called URL safe encode and URL safe decode. And what that does is it just replaces a plus or a / with a dash and an underscore to make it URL safe. Base 64 encoding is actually utilized in many programming languages. It's not specific to Ruby. But to be clear, this is still not encrypting your data. There's nothing secure about it. It's just an encoding for your encoding. It's safe, which means that it's likely to be parsed correctly when you're transmitting data. Okay, so things to remember, today's takeaways. Binary is super cool. Actually, all the number systems are. Remember, there is no such thing as plain text. This is a lie. There's always an encoding. And specify which encodings you accept from your user. You will be so glad that you did that. Please use UTF-8. Keep in mind that characters are abstract entities. They can technically be anything. Think about those emojis you've seen. Correctly parsing a file, any file, requires knowing what encoding was used in its creation. If you guess incorrectly, it could lead to permanent data loss. Okay, thank you so much for your time. I'm happy to take questions and talk more about encoding afterwards. The resources that I used for this talk are listed here so that you can find them when the slides are published online. Thank you.